Hi everyone, welcome to our next lecture in our Material and Energy Balance class. And what we are doing today is putting our ideal and non-ideal gas equations into our material balance questions. So what we have done so far in chapter 5 is looking at solids and liquids and gases, and we saw that to convert between volume to moles or volume to mass, in terms of gases, we actually have to use an equation of state, and the most common one is the ideal gas equation of state. If we deviate from ideal gas behavior, we have to use some more complex non-ideal equations of state that we covered in the last lecture. So now we're going to put everything back into our material balance questions. In this case, just as a starter, for each stream, we think about we're going to draw the process flow diagram and start to label everything. So what's new in this case? For every stream, we need to ask these questions. Is the stream a liquid or a gas? For gas streams, we might need to use the ideal gas law or some equation of state, which means it's going to be a function of temperature and pressure. So in general, I'm going to label the gas streams with the temperature and pressure if we need it. The second question to ask is, are we given any partial pressures? Are we told to find any partial pressures? If so, the only law that we know that involves partial pressures is your Dalton's law. So when you see partial pressures involved, you want to think about Dalton's law that will allow you to find your mole fraction. All right, so that's in terms of the concepts, that's all that's new. So let's just jump into our example. In this case, we're doing example 5.2-5 from the textbook on page 227. Open that up, read the question first, and then follow along as we go over this in the video. All right, in this question, we have liquid acetone that is fed at a rate of 400 liters per minute into a heated chamber. It is evaporated into a nitrogen stream. So you have acetone and nitrogen going into a heated chamber. The gas that leaves the heater is diluted by another nitrogen stream, so you're going to add more nitrogen to that. And this nitrogen stream is measured at a flow rate of 419 meters cubed at standard temperature and pressure per minute. The combined streams go into a compressor, so now you're just increasing the pressure of this gas to a total pressure of 6.3 atmospheres, and this is a gauge pressure, and you're given the temperature of 325 degrees C. The partial pressure of acetone in this stream that comes out of the compressor is 501 millimeters of mercury. Atmospheric pressure is 763 millimeters of mercury. We want to know what is the molar composition of the stream that leaves the compressor, which is the second unit, and the volumetric flow rate of the nitrogen that goes into the evaporator or the heated chamber, if now in this case we're given the temperature and pressure of this stream, the nitrogen stream. So we're going to do this in the same way. Draw the diagram. Label the process flow diagram, do a degree of freedom analysis to see where we can start, and then start to solve this problem. So drawing the skeleton of this process flow chart, we have an evaporator and we have a compressor. In the evaporator, we have an acetone stream that is evaporated into a nitrogen stream. So you have streams 1 and 2. Then you have a combined stream that comes out, stream 3. And this stream 3 is combined with more nitrogen, so that's our stream 4, to give you our input into the compressor, which is our stream 5, and then we're going to increase the pressure, and it gives us our stream 6. All right, so now we have this. Let's go back into the question and start to label or transfer all the information that's given in the question into our diagram. So the first thing we are given is the volumetric flow rate of our acetone going into the chamber, so that's V1 is 400 liters per minute. We are also given stream 4 in terms of standard temperature and pressure, 490 meters cubed per minute. And everything else is given in terms of stream 6. So we're given the outlet temperature, pressure, and we also have the partial pressure of acetone in that stream. So that's all that's given in this question. Now let's go back and fully label this. You'll see that in stream 1, 2, and 4, these are pure streams. Stream 1 is a pure stream of acetone, 2 and 4 are nitrogen, so we only need the molar flow rates of those streams. We don't need compositions. So we have N1, N2, and N4 in those streams. In the other 3 streams, we have a combination of nitrogen and acetone. And so I'm going to label streams 3 and 5 as the molar flow rates of acetone and nitrogen in those streams. You will see that in stream 6, I actually switched the notation or switched the way I label the stream. I label it as the the overall flow rate and the mole fractions. And the reason why I do that for stream 6 is because we're going to use Dalton's law. We have a partial pressure, and Dalton's law gives us the mole fraction of acetone, which means we have to label that stream in terms of a mole fraction rather than an actual molar flow rate of each stream. All right, so here we have our fully labeled diagram. Let's circle our unknowns and now go ahead and do the degree of freedom analysis. We have an overall system, evaporator, compressor, and then we have a mixing point. So we have 4 different systems. Let's start with our overall degree of freedom. We have 6 unknowns. We have N1, N2, N4, and then the 3 unknowns in N6. We have 2 different species, our acetone and nitrogen. We have our 1 constraint, the sum of mole fractions have to sum up to 1 in 6. So there's nothing new at this point. It turns out that in the overall it's going to be 0, and we have 3 different laws in our overall system. So what are the 3 laws? The first one is in stream 1, this is a liquid stream. So in a liquid stream, we covered in our earlier lectures that we're going to assume that the density is more or less constant. So we look up the densities, look up the molecular weights. That will allow us to convert from our volumetric flow rate to our molar flow rate. That's the first law. The second law is that we are given that the stream 4, the volumetric flow rate of nitrogen, is at standard temperature and pressure. So we know that we can convert from the volumetric flow rate to our molar flow rate using the ideal gas law. And the last one is we can use Dalton's law because we're given the partial pressure of acetone in our stream 6. So with that, it gives us a degree of freedom of 0. All right, the 3 laws are really what's new in this lecture. So all the other 3 systems, I'm going to go through it really quickly because the laws are just repeated in these 3 systems. For example, in the evaporator, we have our 4 unknowns in streams 1, 2, and 3. 2 species, and in this case, the only law that applies that we have talked about is in stream 1 because stream 1 is involved with the evaporator. In terms of the compressor, we have our 5 unknowns, 2 in stream 5, 3 in stream 6, 2 species, 1 constraint, and then the only law that applies in this case is Dalton's law in stream 6. And the mixing point, we have our 5 unknowns that I've circled on the diagram, 2 species, and then we have our ideal gas law from stream 4. All right, so we should be able to start with the overall system and then move on to something else and solve everything, solve the entire problem. But in this case, you'll notice what are we asked to solve for? We are asked for the molar flow rates of, or the mole compositions of our stream 6, so the stream that's coming out of the compressor. And we are told to calculate the volumetric flow rate of our nitrogen stream entering the evaporator. In that case, in part B, you'll recall we're given the temperature and pressure. So all we need is N2, YA6, and YN26. All of these are part of the overall system. We do the overall, and that's all. We don't need to move on to solve the rest of the unknowns in this problem. All right, so we only need to solve the overall system. Let's go ahead and start solving it. The degree of freedom is shown up there, which means we are going to solve our 6 unknowns by writing 2 species balances, using our constraint, and writing out 3 different laws. These 6 equations should allow us to solve our 6 unknowns. So we'll start with our ideal gas law. In this case, we know that it is at standard temperature and pressure, so we could put in 1 atmosphere and 0 degrees Celsius, or you could recognize that this quantity down here is essentially your 1 over your V hat S, right? Our specific molar volume at standard conditions. So you can do that replacement over there, and in that case it's easier, 22.4 meters cubed per kilomole, and we can calculate our N4 as 18.71 kilomoles per minute. All right, so we're done with that law. Let's go on to the next law. Let's do Dalton's law. Dalton's law is pretty easy. The mole fraction is just the partial pressure over the overall pressure. Just make sure the units are consistent. In this case, we are told that this 6.3 atmospheres is gauge pressure. So everything in terms of the ideal gas law, Dalton's law, everything should be in absolute pressures, which means we need to add 1 atmosphere to it. And in this case, in the question, we are given that the atmospheric pressure is 763 millimeters of mercury. So we convert that, add 1 atmosphere to that, and we see that the mole fraction of acetone is 0.0903, and that's actually one of the unknowns that we need, right? One of the variables that we are asked to calculate in this question. So now we can use the constraint and take 1 minus of the mole fraction of acetone, get our other variable that we need. All right, so now we have solved for 3 different unknowns by using our Dalton's law, ideal gas law, and our constraint. We're going to solve for our remaining 3 unknowns using the last law for stream 1 and then our 2 species balances. Here's the physical law in 1. We're just going to convert from volume to moles by first converting to mass. So we're going to convert to mass by multiplying it by the density. And then we're going to divide by molecular weight to get our number of moles. How do we get the density? That's from table B1, and you can look up the specific gravity of acetone as 0.791. And so multiplying that by the reference density of 1 gram per centimeter cube, that's how I get my density of acetone. And you know the density of the molecular weight of acetone. Put them all in, make sure the units are consistent, and you end with 5.55 kilomoles per minute of N1 acetone going into the evaporator. All right, we're almost done. We have our two balances left. So let's start with our acetone balance. It's coming in stream 1, it's coming out in stream 6. So it's nice because it's only 2 streams. And the only unknown left in this case is our N6. Put in everything, we can solve for N6. Lastly, we have our last unknown, which is N2. We can do an overall balance. And in this case, you just have one unknown left, and you can solve for N2 of 36.445 kilomoles per minute. We are asked to find the volumetric flow rate of this stream of nitrogen, now given the temperatures and pressures. So now we just use the ideal gas law again, put everything in. In this case, I just converted everything into SI units. So I did it in moles per minute, used 8.314 joules per moles Kelvin for my R, converted my pressure to pascals. And so once that is all done and you put it all in, the SI unit for volume is meters cubed, so we have 551 meters cubed per minute. All right, that's straight up using the ideal gas law. Recall that in the previous lecture, we talked about 2 different methods. Another method is the ratio method. So now we have the ideal gas law for our stream 2, and we also have the ideal gas law under standard conditions. What we're going to do now is just take the ratios, and now you can see ratios of pressures and ratios and temperatures. Why is this method a little easier in terms of the math? Is because the units are a lot easier to deal with. The unit complexities come with R, the gas constant. And now in this case, we have cancelled away the R. So we just have to make sure the pressures are of the same units, temperatures are of the same units, and we'll be okay. So now we're going to rearrange this for V2, which is what we want. We just need to take ratios of temperatures, ratios of pressures, put in all the values. Again, in this case, we are using Kelvin. You can only do it in terms of Kelvin or Rankine. We can keep our pressures in millimeters of mercury. We don't have to convert the units in that case. And now we end up with the same answer of 551 meters cubed per minute. All right, so that's all we have for this lecture, looking at how we're going to put in or use these different laws in our material balance problems. There will be a second video example, so go ahead and look that up, where we'll do a second example putting in using these ideal gas laws in our materials balance questions. So work hard, be smart, and I'll see you in the next lecture.